Hello everyone. Today we group 1 are going to talk about the concept of magnetic flux and magnetic induction in the working principle of DC generator. Our members include Wong Sing Ro, Elvidge Law, E. Houghton, and Bayuk Ling. Sit back and enjoy our video. The two main laws involved in this topic are Faraday's law and Lenz's law.
Faraday's law states that the induced electromotive force in any closed current is equal to the negative of the rate of change of the magnetic flux enclosed by the circuit. Here is the Faraday's law in equation form. We can see that the induced EMF equal to the number of loops times the change in flux over the change in time. Now we're gonna talk about Lenz's law. Lenz's law states the direction of current induced in a conductor by a changing magnetic field will create the field that opposes the change that produces it. It's shown by the negative sign in Faraday's law of induction. This one is the Lenz's law, equation of the Lenz's law. Before we go into working principle of DC generator, we look at single loop generator model first. In this figure, a single loop of conductor of rectangular shape is placed between two different poles of magnet. Let us consider the rectangular loop of conductor is ABCD, which rotates inside the magnetic field. When the loop rotates from its vertical positions to its horizontal positions, it cuts the flux line of the field. As during this movement, AB and CD of the loop will cut the flux line. There will be an EMF induced in these both of the sides AB and BC of the loop. Next, as the loop is closed, there will be a current circulating through the loop. The direction of the current can be determined by framing right-hand rule. The thumb indicates the direction of motion of the conductor, index finger indicates the direction of magnetic field, and middle finger indicates the direction of flow of current through the conductor. Now, if we apply this right-hand rule, we will see at these horizontal positions of the loop, current will flow from point A to point B, and on the other side of the loop, current will flow from point C to point D. Now, if we allow the loop to move further, it will come again to vertical position, but now upper side of the loop will be CD and lower side will be AB. At this position, the tangential motion of the loop is parallel to the flux line of the field. Hence, there will be no question of flux cutting and there will be no current in the loop. If the loop rotates further, it comes again to horizontal position, but now AB side of the loop comes in front of N pole and CD comes in front of S pole. If the loop is continued to rotate about AB axis, every time the side AB comes in front of S pole, the current flows from A to B, and when it comes in front of N pole, the current flows from B to A. As the same, every time the side CD comes in front of S pole, the current flows from point C to point D, and when it comes in front of N pole, the current flows from point D to point C. Now, we are going to talk about working principle of DC generator. Working principle of DC generators is similarity to the working principle of single loop generator. In this figure, the loop is open and connected with a split ring. Split rings are made out of a conducting cylinder which cut into two halves. The external loop terminals are connected with two carbon brushes which are rest on this segment. It is seen that in the first half of the revolution, currents flow away along ABLMCD. For an example, brush number 1 in contact with segment A. In the next half revolution, in the figure the direction of the induced current in the coil is reversed, but at the same time, the position of the segment A and B are also reversed, which result that brush number 1 comes into touch with the segment B. Hence, the current in the load resistance again flows from L to M. The waste from the current through the load circuit is as shown in the figure. This current is unidirectional. This is basic working principle of DC generator and can explain by single loop generator model. The position of brushes of DC generator is shown arranged that the change over the segment A and B from one brush to other takes place when the plane of rotating coils is at the right angle to the plane of the line of force. That is so become in that position, the induced EMF in the coil is zero.
What is magnetic flux? Magnetic flux is the product of the average magnetic field times the perpendicular area that it penetrates. It is basically a quantity of convenience in the statement of Faraday's law and in the discussion of objects like transformers and solenoids. What is induced electromotive force (EMF) in terms of electromagnetism? When magnetic flux changes on an insulator, current will be induced due to the rate of change of magnetic flux. When there is change of magnetic flux, current will be produced. How do we interpret a magnetic flux versus time graph? You guys can have a look at these 4 points and I'll explain further on the next slide. This is a magnetic flux versus time graph. This graph is plotted with units Webers, which is Tesla meter square, against time seconds. Everything here I explained is based on the equation that induced current is directly proportional to the rate of change of Webers over the rate of change of time. When time equals 0, induced current is largest as the gradient of the curve is at its maximum. It is the steepest when the gradient of the curve is at its steepest when it is near 0. I'm sorry that I can't draw on the graph to show you guys, but you can ask if there's any question. Let's continue. Let's assume that when the curve is at its highest, the maximum point, let's assume that's when the time is 5. When time equals to 5, which the flux point is at its highest, current is 0. Why is the current 0? Current is 0 because when the gradient of the curve is at that point, the gradient is at its minimum. Gradient of the slope is 0 at the flux point, which is the highest point. When the curve is dropping from the maximum point, current is also as large as the gradient of the slope. As you can see, when the curve is dropping down, the gradient of the slope is large, which causes the magnitude of the current to be large. It is large, but it is going in the other direction as the curve is going down. Negative and positive. This is a setup of a DC generator. In a DC generator, a split ring commutator is used. Current travels from positive to negative, and in this setup, the current is traveling from the red side to the blue side and back to the voltmeter. When the coil has spun 90 degrees, the carbon brush will not have contact with the commutator. As you can see, there's 2 holes in the commutator. When the coil has rotated more than 90 degrees, the red side will touch the blue side of the carbon brush before, and the colors of the coil will switch. Why will the coil still rotate when it is not touching the carbon brush? This is due to inertia from the force produced before. When the coil is rotating, it will cut the magnetic flux produced by those two magnets, the north and south magnets. And when the magnetic flux is cutting the coil at 90 degrees, the force produced will be maximum. Thank you.
Moving on, we are going to talk about the mathematical equations related to EMF of DC generator. According to Faraday's law of induction, the induced EMF of the armature conductor is denoted by E, which is equal to rate of change of the flux. Equation for the induced EMF of one conductor is E equals to phi p multiplied by N over 60. As for the equation to find the induced EMF in a DC generator, we use the formula E equals to Pz phi N over 60A, where P is the number of poles of the machine, phi is the flux per pole in Weber, Z is the total number of armature conductors, N is the speed of armature in revolution per minute RPM, and A is the number of parallel paths in the armature winding.
Adding more coils will increase the rate of induced EMF because it will also increase the change of magnetic flux per revolution. As you can see in this graph, there are more fluctuations in induced EMF because more coils are changing the magnetic flux. So adding one more coil as shown in this diagram will double the fluctuations from the first graph shown before. When turned 90 degrees, the black coil will turn to vertical, decreasing change of magnetic flux. But the red coil will increase the change of magnetic flux because the red coil is turning from vertical to horizontal, thus more fluctuations in the graph. So increase in rate of change of magnetic flux will cause increase the rate of induced EMF in DC generator.
So modifications that may have been done to conventional DC generator. There are two ways we can do this. First, increase the rate of induced EMF, and the second being reducing the energy losses. So, to increase the rate of induced EMF, we can do this by adding more coils. Adding more coils will increase the change of magnetic flux in each revolution, so the rate of induced EMF increase and a much more frequent and stable current production, as you can see in this graph. And increasing the armature speed can also increase the rate of induced EMF, because increasing the armature speed means rate of turning the coils increases, which will increase the rate of changing of magnetic flux. So this will also increase the rate of induced EMF. And providing a stronger magnetic field will mean that there is a more magnetic field. So in each revolution, the coil will change more magnetic flux, so this will increase the rate of induced EMF. We can reduce the energy losses by reducing the eddy current, the hysteresis losses, and the mechanical losses. So we can reduce the eddy current by constructing armature and cores from laminated layered steel sheets. The laminated sheets are insulated from one another, so that current cannot flow from one sheet to the other. And eddy current is basically the current induced in the armature, and this is caused by when the armature is turning, the EMF is also induced in the armature, so the induced EMF causes a current flow. Yeah. And as for hysteresis losses occur when the armature rotates in the magnetic field, which causes the rotation of magnetic domains in the iron, causes friction and heat. The magnetic domain is basically a region within a magnetic material, in this case an iron, and within the magnetic material in which the magnetic fields of atoms are grouped together and aligned. So to reduce the hysteresis losses, most of the DC armatures are constructed of heat-treated silicon steel, which has an inherently low hysteresis loss, which will also reduces the hysteresis losses to a very low value. And moving on to mechanical losses, we can reduce the mechanical losses by using smooth and clean commutator, and lubrication on the commutator will also help to reduce the friction. So mechanical losses is basically the brush friction on the commutator, and also the air friction, which is caused by the air turbulence due to the armature rotation.